started till now. Now started.
Okay, now we will start.
I would like to welcome all the participants and the resource person for the Atal sponsored 6 days online FTP on recent advancement and challenges in integrating of IoT and 5G and 6G wireless communication, building the next gen connectivity. I would like to welcome Dr. Rajkumar Rangaswamy sir for the today's session. So before going on to the session, there are few instructions for the participants. So today we have three sessions, which has been session one scheduled 2 o'clock to 3:30, and session 2 scheduled from 3:30 to 5 o'clock, and session 3 scheduled from 5 o'clock to 6:30, with a validatory session at last. Participants are asked to check your attendance at the Atal portal, and also after completing the sessions, participants are asked to fill the feedback form at the Atal portal also. If there is any question, any queries regarding, you can contact the coordinators through the WhatsApp. And after completing the validatory session, and participants, you have to attend the test at the Atal portal. The test time starts from 8 o'clock, and you have 25 MCQs. Participants must secure 70% of mark to obtain your certificate. And also, you can check your attendance by 7 o'clock at the Atal portal. If you find any queries with the attendance, you can contact the coordinators through the WhatsApp. Okay, before going on to the session, so let me have a photographic session as per the Atal's protocol. So participants and the resource person are asked to turn on your camera for the photographic session. Participants are asked to turn on their camera for the photographic session. Okay, participants, you can turn off your cameras. Participants are asked to turn off your cameras. Okay, before going on to the session, let me have a short intro about today's resource person. It's my pleasure to introduce our speaker, Dr. Rajkumar Rangaswamy. He is a senior lead at Uno Minda Limited, Chennai. He completed his Bachelor's of Engineering in Electronics and Communication from Arunari College, Arunari Engineering College, Anna University in 2009. And he completed his Master's in Communication Systems from Sona College of Technology in 2011. And he obtained his doctorate from Vellore Institute of Technology, Chennai in 2019. Dr. Rajkumar Rangaswamy has more than 10 years of experience, and he expertise in RF design, antenna development, signal integrity, power integrity, and electromagnetic interference for automotive applications. He has published more than 21 research papers in reputed journals, focusing on metamaterial antennas, compact multiband antennas, and RF component design. Dr. Rajkumar Rangaswamy has an extensive experience in designing compact designs for antennas in wireless applications. We are honored to have him with us today. I would like to call Dr. Rajkumar Rangaswamy sir to take over the session. Please, sir.
Yeah, thank you, sir, for your detailed intro about me.
Thank you, sir.
Yeah, good afternoon to everyone. So, Yuvraj, can we proceed, Yuvraj?
Sir. Yes, sir. You can start, sir.
Yeah, thank you. Can you able to see?
Yes, sir. Your
Yes, sir.
presentation.
Yes, sir.
Yeah. So thank you everyone. Good afternoon. So myself as introduced by Yuva. So I'm Rajkumar, uh, working as a senior lead engineer at Uno Minda Limited. So it's actually the basically automotive company. So we are one of the tier one supplier in India. Uh, we are working on different products, two-wheeler as well as four-wheeler and three-wheelers, from lighting, connected technologies and wireless chargers. Yeah, and for few TCUs. So these are our main thing. Apart from that, we are working on seatings, special electronic seatings and horns. So these are our company profile actually. Yeah. So this is the topic for today's presentation. The recent advancement of multiband and reconfigurable antennas for 5G applications. So this topic contains three topics actually: multiband antenna and reconfigurable and 5G applications. So those two meant for 5G thing. So I have divided the presentation into three sections. One is for uh, multiband and reconfigure how it can be done and how multiband can be achieved and related to the 5G applications. So that's how it proceeded. Uh, there will be the few takeaways. So how recently we did on paper for reconfigurable, that that is somewhat quite we have simulated as well as measured the actual diode based thing. So that is somewhat it can be usable for everywhere. And for multiband technique, that was my PhD topic. So in that, if you have any doubts, you can ask. Okay. So that I have did a multiband antenna for wireless. So here the topic is for cellular. So but we got to combine it over here, cellular and wireless. That is the thing. And finally 5G is we can carry out. If you have any doubts, you can ask, no problem. Yeah. So so we'll start from microwave and multiband. Okay. So here the objective of microwave and microwave is, so here we got to achieve the based on our wavelengths, we got to achieve the compact components. That is the main aim of the microwave. So when it is comes to 5G, so there are various bands are we are using. So from in India we are using around 5 bands, from 7600 to 26 gigahertz. So, but the lower frequency, so in that there are three categories: lower band, mid band, and high band. Okay. So based upon the bands, so the bandwidth will be vary, and based on the bandwidth variability, the speed, whatever things we are realizing, that will vary. That is the difference. Okay. So here in the here for 26 gigahertz, we are touching the millimeter wave. That one design is there. So that one we are touching over here. And why we are going for lump to achieve that one also we're gonna see. Okay. And as I said earlier, so multiband, why we need to go for multiband? So as I explained, there are n number of bands are existing in cellular 5G cellular itself. So in order to combine all the antennas, all the frequencies bands, irrespective of region or country. So suppose here we can take one example of some manufacturer, or suppose you take one you are one of the industry, you are designing one antenna for 5G applications. So you have to consider that application where and all going to be used. That is the very important parameter. Where and all it going to be used, which region and all. Where and all in the sense, which country they are going to use, because country wise the bands are will differ. Okay, that is the important parameter we got to see. That is the first parameter while choosing the antenna for manufacturing. We got to finalize where and all it can be exported and which country locations can be used, because If it is only for India, so we can design for only for Indian bands. If it is only for USA, you can design for only for North America. So in that way, we got to design the antennas over here. So because cost is another constraint when you're coming for the designing the things. Whenever we are doing for only for proto purpose in the sense only for the particular band wise, that won't make sense actually. The problem when it comes is when we are going to implement in the real-time environment, then only the problem will come to the picture, because measuring the written loss, radiation parameters like VSWR, radiation patterns, gain, efficiency, those and all will be there. That is a basic characteristics. Apart from that, there are a huge number of parameters are there, because bandwidth interoperability will be there, because what are the 5G you are using, you should not interoperate with the interference with the 4G or other existing cellulars or other existing wireless communications. So those are the very, very important thing. So here, to accommodate all the antennas, all the applications or requirement in a single band, we are going to adopt the technique called multi-band. So in the multi-band, there are two things will be there. One is the wider conventional size multi-band. That one can be done by anyone, but that won't be the give the impact for our whatever the research we are performing. So when we are performing or about to do the research, what is the market demand? Okay, you got to take the benchmark in the sense literature survey while you are performing, not only the research purpose. So our research should focus towards the industry. Then only we can able to meet the current demand. Okay, so it will be easy for us to move to academia to industry, or academia and industry collaboration can happen easily. So people can support from academia to industry collaboration in terms of how it can be done, solution can be provided. So here the multiband in the sense, first antenna should be very compact and it should support for all the bands. That is the thing, all the bands. Suppose the customer comes, so they will ask for, can you give me the antenna of 5G for all the bands? So you got to define it like whether it is mid band or lower band or only for high frequency or 26 GHz, that is a millimeter wave. So in this way, we got to narrow down, we got to start to work. So that is one of the very, very important thing. That is the purpose multiband will fulfill. So when you want to have the compact technology, you can use any technique. So here I have taken the example of metamaterial. This is metamaterial is one of the proven technology or proven technique which can be used for obtaining the compact size. I think you might seen so many literatures whoever works on or deals with the antenna technique. So because the metamaterial is the category comes to the picture when the meta cell wavelength is less than lambda by 10. Okay, then only it can be called as a metamaterial. Usually we'll for monopole antennas we deal with lambda by 4 structure, but here the not whole antenna, meta cell alone. So this is the reconfigurable we'll see later. So these are the these applications we're going to implement in the our 5G thing. Okay, and this one reconfigurable will touch when we come to the reconfigurable part. So why we are coming for 5G is we knew that the first thing is speed and reliability and data sharing. That is a very, very important thing for 5G. So this is the evolution chart of 5G, how it is growth happened from previous decades to forthcoming decades. Okay, so the speed going to be the increase because customer requirement is the customer satisfaction requirement is a very priority goal. So for that only we gotta work. Yeah. So currently we started to realizing the 5G, but not fully 26 GHz. We are using the mid bands. So these are the things we are realizing. Directly we'll get into some of the applications. So these things can be realized using the 5G. So here, one example I will give you by this this picture or this slide. We are working for one of the product. Okay, So in the product, there are evolution happened in the particular product. So that is a TCU, telecommunication unit. So in that, normally we before half a decade, we used Bluetooth, 2G antenna, 2G and GPS. These are the three were there. Okay, for tracking and communicating to the user how where and all trackability and for the purpose. But recently, few years back, okay, we developed one product. Okay, it is in the market. So in the product, we are giving 4G diversity antenna. So not a single antenna, 4G diversity antenna for one product. For one product, only the single antenna. Okay, and same Bluetooth 5.2 and GNSS. So why we are using diversity and 4G and all? So in order to accommodate the customer satisfaction and the reliability, the speed should be very high and data communication needs to be done. What are the data they wanted looking for? It needs to be done, right? So that's the purpose we had to work. So similarly, for the forthcoming designs, the OEMs, the Indian OEMs as well as the foreign OEMs, they started to ask for 5G based the same application. What are the things we developed? So they're looking for with the integration of 5G. So these things gonna be changed constantly, but the technique, so we gotta adapt how and all it can be done, how and all it can be increased in terms of speed wise we cannot do it, but how it can be made compact in terms of antenna wise, how it can be integrated into the vehicle. Okay, so antenna when you're into the integrating into the vehicle, it is around 10% of the thing. Okay, the remaining hardware, software, everything gonna be takes place. That is a very important thing. So these are the efficiencies for all the purpose. So this is the for connected, as I said, right? So for all the things for the communication only, we are going for 5G. The main purpose is speed. Yeah, this and all some core thing. So how and all it can be done? Okay, MIMO, as I said, MIMO. That's why we are using for 4G. Also, we started to use for diversity-based antennas. Okay, it can be in order to have multiple things. So whenever there is a loss from another antenna, you can able to manage the data transfers. So the process will happen without any hiccups. So similar way, it's going to be the grown up. Okay, the 4G onward, 4G, 5G like that. That's why we are using the MIMO concept over here. Yeah, this and all can be used for 4G or what how and all we are using. So as I said, why we are using we are used diversity based antenna because of number of antennas will be used. The data loss should be very less. So that's why we are using for diversity or MIMO. For similarly, you can see how many elements are we are using to cater the data loss or to give the more number of data. That's the reason we are going for this one. And how we are getting more bandwidth and speed. This is the main thing. Yeah, this is the main thing. Because of elements, we can able to even though there is a fading and everything, so we can able to get a proper signal, and strength of the signal also will be higher. So we can able to get a or fulfill our desired application with the desired speed. Yeah. So these are the things. Yeah. So what are the things we seen? The range. So 5G does have a few drawback. So it cannot be covered for the larger area. It will be for the short range communications. That is the limitations. So as I said earlier, so these are the bands actually you are using in India. So here we can focus these areas actually. Whenever whoever wants to work on reconfigurable based antennas, they cannot combine 26 in the 3300. It's a very huge one. You can combine easily lower band and mid band or within the lower band. So the reconfigurable can be done on this one. Yeah. So this is why we are coming for multiband. We already see. Yeah. So this is the one of the work. So we are getting into the work based thing first. As I said earlier, we'll see the multiband, then we will see the reconfigurable, then we will see the 5G. Yeah. So why we wanted multiband? In order to cater the desired necessity of all the applications, we need to have the single antenna so it can fulfill all the necessities, right? That's the purpose we want to have the multiband. That's the first one. Second one should be the same antenna should be compact. It should be integratable. Okay, this is the second parameter. And what and all, or where and all it can be implementable, supportable. Okay, and fourth point is the affordability, whether it can be expandable to the higher frequencies, or it can be is there limited with the only frequencies. Okay, so those things also I can share. Okay, what is the difference will be there when we are going to the real-time environment. So this is the one of the research paper uh, deals with a compact multiband antenna using the metamaterial technique. So this paper deals with the triple band antenna. Triple band. This is it's for yeah, you can see over here how it is evaluated and everything. So this is the antenna evaluation you might see in here. So that part, yeah. So how it and all, because you can see the antennas. This is actually one of the Elsevier AEU, I think, yeah, electronics and communication engineering. And comes, I think, comes into the SEA based one. So the antenna size is actually 27 cross 23 mm square with a thickness of 1.6 mm. This is made up of for actually FR4. Okay, so it covers till 8, but when you want to go for this is the thing we implemented but it is not in the, what to say, it's not in the real world actually. Okay, it is there in the research wise. So when the work comes to the real world, okay, so 1 minute, yeah. So this is made up of FR4. I think you people are familiar with that. So the FR4 does have the high loss tangent, so lossy material. So people are people in the sense the real time thing, we should not recommended to use the FR4 for more than 6 gigahertz. That is a recommendation. Okay, suppose if you want to realize that what do they 26 gigahertz, okay, 5G or millimeter wave communication. So you should not use the what to say FR4 here, because when the frequency increases, the loss tangents also will increase. Okay, these two are directly proportional. So while choosing the materials also matters over here. Okay, while choosing the material, we got to focus that this. Give me a minute. Yeah. So while choosing the material also, we got to focus that whether that material withstand the quality of the material will be sustained till 26 gigahertz or till 12 gigahertz. So those kind of analysis we got to perform before starting our design phase. In the design phase itself, we got to design whether we're going to limit only for lower frequencies or we're going to expand it to the higher frequency also. So those things we got to check it over here. Okay. So here we are dealing with FR4 antenna till 8 gigahertz. Okay. So this is the iteration we have performed. Tapering. Tapering is one of the technology how it can be obtained to the multiband. So since the topic is reveals the multiband, discuss the multiband, we are talking about how it can be multiband can be created. Okay, so you can see here the A is designed for 5 gigahertz. Okay, and the B, this is the splitting, and we are introduced a loop. So there is a when the loop length increases, it tends to go towards the lower frequency because these two are inversely proportional over here. So you can see the slight shift in the B and the C. This is the tapered method. This is the one of the method meant for increasing the bandwidth and attaining the multiband response. So you can see the existing band from 5 gigahertz to it's moved around for 3.5 and 7. Okay, and similarly when we are introducing one more loop, okay, metamaterial based loop, So we are able to get another frequency at 2.4, that is a ISM band, and here the 3 from 3 megahertz to 6, that is a wider band that covers uh, all the wireless LAN bands and all the modern 5G bands also over there, and this ITU band. Okay, and finally when we are connecting that, we are able to get an impedance match. So you can see that there is some improvement in the S11. Okay, so this is how so here the multiband technique is given as an evolution, but whenever we wanted to implement in our particular work or scenario, we gotta go for survey, literature survey, and what are the methods or technology suitable for us. We have to adopt the particular technique and to get a realize the multi-band performance. So it could be anything. Okay, the application here, the application is 5G. So as I said, so this band, okay, this band is realized for all the three, from 3 to 6 gigahertz, right? So you can cover all the 5G also you can able to cover. If you want to increase, the same antenna can be tuned for lower frequencies. Okay, that covers the existing lower band. What are the things existing in India? Okay, so those things also you can try with the same kind of a reference by changing the stubs over here. You can able to shift, as I said earlier. Then you can realize the lower band and with a middle band. Okay, for the 5G things except 26 gigahertz. So this is how we can start to realize one band. So here we have done optimization. We have done optimization for each parameter. So what are the so when you are taking the any parameter here, so here the parameters, so here this is called the G, okay, this length, so whatever the thing. So how it will vary, okay, when you are optimizing the G, how the responses will be towards the your desired S11 performances. So those things needs to be analyzed, and by keeping other parameters constant. So you got to check one by one, and we got to finalize the parameter. This is the basic way to finalize the parameters, because we knew that what going to be our desired frequencies, because we are having the frequency bands and their bandwidths. Okay, so based on that we got to optimize it. So here, and one more thing is, since we are dealing with the how to say cellular thing, for non-cellular we got to go with the 10 dB. Okay, for the cellular it can be low also, so though no problem. So 6 we used to maintain. Okay, so that one also works. For that is a difference between cellular and a non-cellular. And for cellular and non-cellular, there are measurement techniques also will be different when the product is done. Not only not this R performances, when you are integrating with the actual what to say actual hardware, that time we gotta check whether compatible test is there or not, interference is there or not. Those things, that time when you so that one they will call us a signaling and non-signaling test for cellular and non-cellular. So that those things needs to be carried out. So these are the things. Yeah. So this is the results for the particular work for the multiband. You can see. So it covers from around 3 to 6 gigahertz. Yeah, around 6 gigahertz. Yeah. So these kind of deviations are maximum cases are expected because the simulation environment and real-time actual environment going to be the different. Okay. So with a deviation of 10 to 15% over here, it is accepted. And yeah, one more thing we'll discuss. Yeah, these are the radiation pattern. What are the things we measured over here? Yeah. Yeah, this is again. So as I said earlier, this is are meant for what to say wireless. As I said, that non-cellular thing. So it's going to be for short range communications. Okay. So we got to understand that that's what when we are started to design, we got to we got to finalize whether our application going to be for what range, how much distance it needs to cover. Okay, how much should be the dBm in terms of receiver, how much it should be, if it is should be higher or lower. So all those information we should have in terms of product wise. So here you can see the gain is low. Yes, gain is low here. Yeah. So here, and one more thing. So for this one for particular slide, and yeah, this slide we are having. I'll give one more uh, uh, experience. Whatever thing I have come across, I'll share. So this is the one of the extraction parameters when you are saying the metamaterial for achieving the compactness. You got to justify or prove that particular metamaterial based cell does contains the uh, metamaterial property. That is, it could be negative permeability or permeability or both. Okay, so we got to justify that it is having the particular thing. So this is the particular analysis called extraction of negative permeability. So by this one only, it can be justified. So the reviewers or the research community will accept the particular work as the metamaterial based one. Even though without justification we are trying to claim, the acceptance won't be there. So while yeah, while going for the meta, if you are going for you are choosing the metamaterial, so try to prove this particular thing. Okay, yeah, yeah, I would like to add one more point over here. Yes, yeah, yes, yeah. So here, yeah, normally when we are doing the normal research, what we used to do is we design only the antenna. Maximum time we used to miss. Okay, it's not a mistake. We used to miss. Okay, where we are missing is the antenna alone won't give the impact. Okay, so antenna plus matching network is needed. That is the very important thing. So while designing the antenna, we should have the matching network. So why we need a matching network here is uh, anyhow. So what are the, it could be the what are the GPS tracking or whatever thing we are releasing. Okay, or mobile phone, whatever it is. So we are having the enclosure. Okay, that enclosure will be maximum of uh, acrylic based or ABS uh, based plastic materials. Those plastic materials will contain the carbon. So that carbon, if the carbon impurity is higher, or whatever the RF radiation, okay, comes from the antenna, it is started to reduce. Okay, the strength of the antenna waves will be reduced. So what we are doing is reduced, and one more thing will happen is shifting will happen. Okay, you might be seen that when you are touching your antenna with your hand, or putting any material to the antenna while measuring the VNA or in the radiation or in the chamber, anechoic chamber, you might seen in the resonance shift. Okay, so that is the thing will happen all the cases. Okay, so what we gotta do is we gotta go for a matching network before see uh, okay, so before here, okay, before this is the antenna. So before here we got a matching, we should have matching network, and here we should have the port in the sense 50 ohm we gotta pump it. So first thing is we should have the matching network. Even though there is no shift, no problem. If there is a shift, so as an engineer, RF engineer, we got to work on the tuning. That is called matching network tuning, or RF tuning. We got to tune it, then bring it to the antenna as a workable for the real-time environment. Okay. In some cases, what will happen for the TPMS? There is a application called the tire pressure monitoring system. Okay, how much at tire is there in our vehicle, so we can see through the Bluetooth. Okay, so that time what they'll do is there will be enclosure, there will be the potting material, there will be the wheel rim and tire. Okay, so everything will be there. So when you are doing the planar antenna, it won't work over there. So matching network is mandatory over there. That is the first point. Okay, So we can tune it because we are adding the rim. There is a metal part. We are adding the tire. There is a rubber part. Tire used to have the copper also. Copper in the sense, the wires will be there. You maybe metal wires will be there in the tire in between, right? So those things definitely will impact our RF performances. So those things also we need to take care while we are designing. So that's the purpose of matching network. Okay. And one more thing is here you might see here and here. So this is how. So application you got to see. So here this is a lower, very low. Okay. If you're getting minus 0 dBm or no problem, but that case should not be the for the cellular case. If it is non-cellular case, your application is 0 dBm or minus 2, no problem, because for Bluetooth, first we'll finish up this. So those cases no problem, because whatever the thing we are pumping from this antenna, right, in the actual environment, application wise, it could be what to say, TPMS, or it could be the for two-wheeler tracking application, whatever it is. So there will be the chip for Bluetooth, there will be separate chip, there will be a separate chip for 4G, all the chips will be there. In the chip, you can able to induce the power. Okay, that is advantage for the designers. So you can able to induce the power. So from it can be varied from 0 dBm to 8 dBm. Okay, so that much input power you can pump it through the antenna. So we can able to work how it can be. Okay, with the 0 dBm, if you're able to work, fine. So we should not go 8 dBm, then your design is very poor. So we can go for 2 dBm. Okay, maximum 3 dBm we can go, because when you're going for more dBm, another problem will come. What's the problem is power consumption will start to more will start to increase. So if you have the battery life will go down automatically. So that's why. So these are the parameters are there. So we gotta take and we gotta play. Okay. So you can take the research topic on the particular aspect also. So suppose I'm instead of using 3 dBm, how we can reduce the 0 dBm, how it can be done. Okay. So those things can be taken as a small topic and we can work actually. Yeah. So that is the one thing. So while real-time environment, you should see where it's to be implemented, whether it is for short communication purpose or longer communication purpose. See, if you are using for only TPMS, you should give only for 3 meters or 4 meters. Okay, maximum, that is insufficient. That is a user will sit on the car or two-wheeler. They want to realize. So, okay, with the metal vehicle environment, if you're able to give 5 meters, that is more than sufficient. Okay, no need to go for the Bluetooth actual. So nowadays the Bluetooth go for 30 meters also, right? So 30 meters, 40 meters is going without interference. It goes more than that also. So those things are not no need to realize. So here you no need to pump the 8 dBm. Okay, so your application needs only for 5 meters. Then you can reduce the power. No need to waste the power. No need to keep even the 2 dBm also. You can stop your power with a 0 dBm. Okay, that is sufficient. So that cases only the gain will what do they start to contribute towards the. That's why whenever we are asking the gain, why we need a proper gain. Okay, but for cellular case you need to have the even though there is a thing, but for Bluetooth also, if you want to transmit for 50 meters or 40 meters, then you should have a proper gain. Okay, so the gain should be more than 4. That's a dependent. Okay, that's not for all the cases, but you can add condition. With the condition you can add. Yeah, that point I would like to clear. Okay, so you can whenever you come across any research papers or research work, you can concentrate on a particular parameter also. So you can, it will be easy. And one more thing is, the reconfigurable thing. This is a reconfigurable antenna. So why we need to go for reconfigurable antennas? So the same antenna should work for multiple frequencies, okay, without changing the antenna. So suppose sometimes what will happen if you're not able to accommodate n number of antennas for n number of applications. So that's why we are going for multiband. So other technique is the same antenna can be used for one frequency when is the diode or whatever it is on. If it is off, for another frequency. Okay, so those things can be controlled externally, needs to be controlled. We got to bias the DC, we got to provide the power separately, and we got to control. That is the purpose of reconfigurable. So reconfigurable will avoid extra antennas. That is the main purpose. So it saves a lot of space, it saves a lot of cost. Okay, this is the reconfigurable antenna. So purpose. Okay, then how we gonna achieve it? That is another thing. How we gonna achieve it, and what are the things can be implemented to realize the reconfigurable? So here n number of things are there. So you can see here, pin diode, FET, MEM switches. So what are the examples we have took? So the conventional pin diode. So this is the one of the work. So this is meant for multiband antenna. So here what we used is, so we designed antenna. So here we implemented diodes, pin diodes. You can see over here. So I'll share with the part numbers. If anybody interested, please check with Yuvraj, the coordinator of the particular FDP. So you can share you. So this is the particular diodes. So here what we are doing is, you gotta give the power supply, you gotta power it. So when it is on, okay, what are things it should happen? So it is defined it. When it is off, what are the frequencies should be on and off? It's defined it. So so before coming to the implementation part, how we gotta do? So we gotta define the frequencies first. Then we got to work on how many frequency shifts we needed, whether it is 2 frequencies or three frequencies. So that one can be decided by our necessity or a requirement. Okay, so here we are used two diodes, pin diodes. So you can see here, this is the thing we solved. So before coming to the particular thing, so you can try to simulate in the EM simulators like ANSYS, HFSS or CST. Then if you come to the implementation part, it will be very easy, and there is a high chances of getting accepted. So when you are implemented with all the actual photograph recordings of how it functioning, so it will be very easy for reviewers when it comes. Suppose you are applying for the any kind of funding thing, so it will be easy for them to get a knowledge on that, how the works. So this is how we are checking. So you can see here antenna, and so antenna is mounted, antenna is containing the diodes, okay, pin diodes. So you can see power supply we are feeding over here from here, okay, and based on the power supply of pin diode, how much is required to operate. So that one dependent on the pin diodes. So you can refer the data sheet of the pin diode before providing the power, then start to record it. Okay, how the changes when it's off condition, what is the difference? When it is on, what is the difference? So those things can be recorded. So here, yeah, this is the done in simulation. This is the done actual model. Okay, measurement model. So this is the simulated model. As I said earlier, so we gotta fix it. Okay, so what are the conditions we gotta go in the pin diodes? Okay, one is on condition and off condition. Okay, what is how to make on and off in the simulation model? So you have the antenna. I think most of the people may work HFSS or CST. So both simulators having this feasibility to import from the 3D model to 2D model. So this is the 3D model. It's simulated model. So there you can see all the 3D best performance, the radiation pattern, efficient, all the things. So the 3D gain and everything you can see, and you see the normal 2D performance like S11, VSWR, everything you can realize that. So that model is implemented directly from the 3D to 2D. So in 2D, what you can do is you can create this particular environment. Okay, so see, since you wanna realize the particular reconfigurable thing, you can start to model it. How it can be modeled. So for on condition, how it should be. For based on the diode, you gotta use it this one. Okay, for on how it is. For off condition, how it should be. So this is for off condition. Okay, so we are implementing here for off condition. So here this picture is given for this condition on and off. So similar way you can implement for all the conditions. Suppose this is only for two diodes, right? So we are having the four scenarios. If you are having three, it will get improved. It will get 4, 6. So it will keep goes, right? So you can have the multi-reconfigurable antenna. So such a way you can design it. You can try to realize, and you can able to capture the responses, how the S1 performance is very okay, all those things. So while we are implementing or while we are writing any research article, if we are able to give these kind of a full information, okay, with the actual measurement, okay, with the actual details of the pin diode, how it is before pin diode, how it was after the implementation, how it got shifted. So there is a high chances of, see, we are able to correlate, right, how it can be. Yes, this is how it will be. Yes, correct. So how it can be earned, how it can, detailed explanation will help even for our understanding as well as evaluators also. Easy, it will be easy for them. So this is the S1 response for each one for all the three cases. Okay, all the four cases, how it was. So here we implemented the second case number 2. Sorry, on and off. Yeah, on and off. That is our requirement. So we are able to achieve the thing. So this is how this is the multiband reconfigurable. So as I said earlier, the topic is given as a combination of multiband reconfigurable for 5G. Okay, so that's why we are going the splitted manner. So if you are able to combine, that's what the first application you can take multiband. So in the multiband you can implement the same kind of pin diodes. Then you can able to realize the lower and mid 5G bands. So it will be quite good work. Yeah. So this is the work for the thing. Now we are moving to the 5G millimeter wave applications. Okay. So even here in the millimeter wave, as we seen previously, there are a number of bands were there from lower bands from 600, 700, 2.2, 2.6, and 3.3, 26. So here we gonna focus on higher band. So among the existing spectrum, you can see from here, okay, 32 here. So those things are totally related with the wavelengths, okay, and the higher number of frequencies, 26 gigahertz. That is the existing band, last band for 5G. That is the millimeter wave frequency. Why it is millimeter? Because of the wavelength. Okay, nothing. Why it is millimeter means the wavelength is very short. That's the reason we are calling that frequency as a millimeter wave frequency. Yeah. So, and one more thing here is, yeah. So I think we people are aware that since we've seen multiple combinations so far, when the frequencies increases, the antenna size also will get to the shorter form. Okay, shorter in the sense smaller, because these two are inversely proportional. So that combination we can able to realize. Okay, yeah. So here this is chip or PCB. That's why we are calling as a PCB in the sense substrate based work. That is calling as a PCB thing. Why we get into the particular thing? How we can able to realize the 5G. So 5G of thing. So these are the main thing for realizing the millimeter wave applications. Yeah. So what are the spectrum in millimeter wave? These are the spectrum other than the 26 megahertz. So these are the bands are available in the millimeter wave communications. So you can see here, these are the bands, and what are the bands are existing for thing. Okay, so this is taken for ISM band, and these two are bands are allocated in the radar. So this is the one of the forthcoming technology. So in many four-wheelers they started to implement. Okay, I think many people might see in the high-end cars. Okay, so they might be started to see this 24 gigahertz based radar. Okay, so this work will comes with. So we are having the side mirror, right? So side mirror will have contain the cameras, and top of the vehicle also, I'm saying for the four-wheeler, okay, top of the vehicle also will have the camera. So all the cameras, and backside also will be there two cameras. So the 5 cameras will be connected to this display unit, okay, that is the central part unit. Then from there the radar will take care, okay, how much area it will cover, is there anyone is crossing the thing, okay. So that one, this one is they're using for ADAS technology maximum thing in automotive thing. Yeah. Yeah. So why we need to have the MIMO? We already seen why we existing. Why we need to have a diversity based antennas. Okay. So this is a very important thing. Why we need to have the decoupling? This is the, because when the two antennas are what to say, resonating with each other, we should have decoupling. Is nothing but isolation. Okay. Isolating or separating the two antennas or two antennas resonant frequencies, we are separating, okay. It should not be the interferences between these two. So that's why we are isolating the two antennas. So for isolating the things, there are n number of techniques are there, okay. So it could be, you can use the EBG based techniques, or metamaterial. If you take metamaterial, there are n number of things are there, or you can use the strip based things also. So suppose if you want to do for wireless LAN, 2.4 gigahertz. So after designing that, if you're on separated, but the area is very compact, you got that time only we got to use the technique, okay. So when we are not using the technology, the size of the what is it, PCB or the area will be huge. So that's the reason we are trying to implement the technology to have the same application with compact size. So okay, that is the requirement. So we gotta work, as I said, stressed earlier. So we gotta work based on the requirement. So for the requirements, we need to adopt various technologies. Okay. So these are the technologies can be done for isolating. So for isolating or decoupling, okay, there are n number of things are there. So you can realize. So this is the, when you're taking the MIMO, these are the parameters. Suppose anyone designs MIMO antenna, these parameters should be present. Okay, isolation and return loss, and S21, another S21 will measure the isolation. So all the things should be implemented. So when you're going for MIMO, so this is how we implement, right? So for electrically small antenna should be, since we are designing for 26 gigahertz electrically small antenna, there is a we can, if anyone wants thing, the first work, whatever thing I mentioned, right, that work deals with electrically small antenna. So that there is one justification, whatever thing we are realizing for metamaterial based antennas. So here also, if you are adding the term electrically small antenna, we got to give a justification, okay. So in that the researchers already they done and they proved how should be, okay, how should be the what is the meaning of electrically small antenna. We got to prove that particular theory for our particular antenna, then only we can, then if it is meets, okay, if it is a criteria meets less than 1, okay, then only the antenna will be called as a electrically small antenna. So here this is for particular technology. So this work is realized based on the SAW compared to the conventional microstrip based technology. The SAW is very better technique. So here it will act as a waveguide, the same kind of thing. So see here. So what are the waves of propagating over here? It cannot able to leak outside of the thing because we are using the wires over here. So those wires will act as a barriers, okay, those will act as a barriers, and for these things there is separate calculations are there. So based on the frequency, whatever thing we are pumping over here, those things needs to be designed. So other side, without any loss, you can able to realize, okay, that is the purpose of SI wave technology. That's why we are preferring this technology. The same thing you may see in the Faraday caging, okay, Faraday steel cage, and okay, that is a technique. Suppose there is a PCB, so in the PCB there is a what to say, there is an antenna, okay. If antenna is there, there will be the stitching will be there. This kind of a stitching will be there, okay. Stitching or wires, okay. They will call it stitching wires in actual PCBs. So those things they will implement in the actual board, that is meant for the same purpose. So that purpose, whatever the SI wave does, that one also does same thing. So both are interrelated in terms of purpose wise. Okay, that's the reason we are going. So this is how microstrip technology, how it works, and when it goes for uh, SI wave, how it will be. Okay, so this is the normal planar one, but how it is SI wave it will work. Okay, yeah, this is the reason. So this is essentially hybrid of microstrip and dielectric thing. So in the microstrip thing, we will use a conventional one, but the advantages will be very last. That one will have more lossy, but here it will be very less lossy compared to the microstrip technology or coupler and whatever the technology without using any wires. So this is the requirement. We already know this is isolation parameter. Sorry, how much should be. So this is the first criteria, not only for the research. Wherever you are implementing any antennas, okay, antennas are implementing nearer to each other. You gotta take the antennas lower frequency of each. If it is same antenna, no issues. If you're using two different antennas in the sense two different applications, you gotta take the suppose if you are using GNSS, okay, we gotta take 1.575 and we are using the Bluetooth 2.45. Okay, these two applications we gotta take. Then we gotta find out the wavelength. Then we gotta find out the distance, how much it should be. Okay, then only it can be realizable. So here this works deals with what to say 26 gigahertz. They implemented actually using the RT Durite. Already we mentioned that why we need to go for what to say 26 gigahertz. Why we need to use the RT Durite. Okay, that's the purpose. So this is how they implemented. For there are lower frequencies. For lower frequency, they implemented with a FR4. For higher frequencies, how it is. Okay, 2 cross. So 26 gigahertz we are covering over here, and how the measurements and all. So this is called a memo from single element to two element and two to four element. Okay, so for this is the thing we should we already we have an idea, right? So here we should have all the thing the 180 degree with each feeding should be 180 degree opposite each other because of there is a reason called isolation as well as diversity antennas should be placed opposite to each other. That is the reason we are placing the antennas in such a way. Orientation is we are arranging in such a way to have the proper thing. Yeah. So this is the radiation performances. How we are implemented. You can see the RT Durite how much is the it is having, and similarly you can see conventional SMA cannot be used. You have the different SMAs for higher frequencies. That's a bit costlier, but no, we should not use. We gotta use that one only. That intended application needs to be realized with intended connectors because these connectors started to degrade when it is beyond the 18 they given, but when it is crosses 15, it started to performance started to degrade. So this is the realization. Yeah. So you can see the S11 and the isolations parameter. Okay, 1, 3 and this thing simulated and measured. So it should be less than 30, sorry 15. It is we are having good compared to the limitations. Yeah. So when it comes to the millimeter wave, these are the limitations. High cost connectors, you got to use better connectors and substrate. RT Durite substrates are quite costlier, but you can when there is you can write a letter. Actually, you can write letter to the RT Durite manufacturing the USA team. Okay, with the approval of your college or university head approval, we can write to them. they will provide the free sample. So you got to give your requirement, what is the size and everything. So they will provide you a free samples actually that RT do right. Okay, so you can try, you can save some quite penny over there. Yeah, yeah. So that's the way we can. First sample they will give free. Uh, Please check. Yeah, first sample. If you are first person apply from your university, they will give you the at a free of cost. But they wanted the have some kind of a the letter recommendation letter, or so in that you got a recommendation letter from your higher authority of your university. Then you can go for it. So yeah, that's the limitations and the fabrication things as I said earlier. So last engine of substrate, dielectric class. So all those things you need to see. You got to look into it. Okay. So yeah, that's it. Yeah, that's it. You have and main thing is what other thing we discussed. It could be like a enclosure thing. So the antenna, if you're implementing, try to go with the enclosure because the real time antennas will be there with the enclosure. Okay, so we gotta you can move ahead with the enclosure. Okay, so while choosing enclosure, you can what to say, you can do the literature survey. So how to choose the enclosures for particular applications. Okay, how much carbon content is allowed to choose this particular application. So those things and all you gotta come into the picture. Next one, you gotta look into the matching network. How is the matching network? Why we need to have the matching network? Okay, whether it is the single stage matching network is sufficient or dual stage needed. Okay, because when you're going to have four or five or 4G, we are having 6 bands, right? So under those particular cases, single band cannot be able to justify the thing. So that cases you gotta have a dual stage filtering. Okay, matching network, and that's the one thing. And the gain parameter, how the gain is very important. Whether it is for how the gain it's varies is whether it is the short communication or long communication. Okay, whether it is cellular or non-cellular. Okay, and though dependent on the implementation environment alone, the antenna factors or antenna parameters will be decided. If the antenna implementation is requires very stringent thing, we got to go for it. No other way. So that time we got to choose whether the particular material withstand 85 degrees Celsius or not, whether it will withstand minus 30 degrees Celsius or not. So we gotta ask our requirement, whoever giving the requirement. So we gotta check, or we gotta tune our research work so it can be implemented globally. So it can support Kashmir as well as Canada. It can support for Tar, Rajasthan, Tar. So because over there we are reaching 40 degrees Celsius, right? 40 or 45 degrees Celsius in summer. So these extreme climates, we need to take care and we work. But within south, we will maximum reach 30, 38, maximum 40. But in over there, we can reach 40, 50 also. So those extreme situation also our PCB performance which should withstand and you should work. So this is the another takeaway or needs to be implemented. And another thing is how the reconfigurable should be implemented. So the enclosure gain part, all the things are mandatory. Along with this, the reconfigurability, you can use conventional pin diodes. Go with the data sheet. All the details will be provided. How much voltage is required for on condition, off condition. So and how many frequency shifting you would like to see, whether 2, 3, 4. That so you can decide with your component. It could be pin diode or FET or directed. So whatever thing you wanted. Okay, you can choose that one also. So you can choose the application. So reconfigurable with the multiband with the 5G is the feasible one. So first you got to design the multiband antenna for 5G for mid and lower band. Then implement with a reconfigurable. Then it's over. Okay. So already, so in this way, in this evaluation way, if you goes, The except 26, you can implement everything easily in a single antenna. That's what I'm saying. And when it is coming for 5G, so 5G of what about the cellular? Okay, 4G to 5G. So you got to look into the frequency first. How many bands we gonna cover it? Okay, no need to cover all the bands. So you can explicitly you can write up. So we are covering this regional bands, not only the Indian bands. So that won't give a sense. So you can cover with the Asia bands like that. You can specific wise you can do it. So they may say home allocation test and automotive thing. So that is nothing but so particular test or validation needs to be done for regional wise. Suppose the particular product goes for Europe, they will do different kind of a test. If it goes to North America, they will do different kind of test. If they goes to South Africa, they will do ICASA. If it goes Brazil, they will do Anatel. So these kind of a different test they will validate for a single same product. So that's how we got to what to say. We got to mention it explicitly to the research community, and we can claim no problem, no issues in this. By putting explicitly, not it won't be the issue. If they are, then only they will ask us. Will you able to go support for another region also? Whether your antenna will support. That time we can say that yes, the same antenna can be supported for another region also. We are trying to another works comes as a we are trying to implement with a reconfigurable antenna. So this is how we got to how to say we got to expand our work. Not only we should not stagnate in one place. We got to shift. Suppose the work is only focus on 2.6. Suppose the requirement another 5G band is at 2.3 or 2.1. So the same band can be obtained through the reconfigure technique. Then it will be fine. So yeah, this will be give a perfect evolution to the technology, whatever things we have discussed. Yeah, I'm done. Yeah, if you have any questions, you can ask.
Participants, if you have any queries, you can unmute yourself and discuss your query with the resource person now. I repeat again, participants, if you have any queries, you can unmute yourself and discuss with the resource person now.
Good afternoon, sir.
Yes, sir. Yeah.
Sir, from the starting of the day, we have heard that metamaterial is the important for antenna fabrication. Whether any other material is important for that, sir?
No. Yeah, sir. Sorry, sir. No, sir. Metamaterial is nothing but is a structural oriented, sir. This is the. Can we go deeper, sir? Is it okay, Mari, sir?
No problem, sir. No problem.
Yeah, yes. So whatever the thing, I'm sharing my screen, sir. Okay. So
Yes, sir. Yes, sir.
yeah, I will look. Yeah. So, sir, Mari, sir, is it visible?
Yes, sir.
Yeah. So, what are the structure we have drawn? Sorry. What are the structure we have drawn, right? Like this, we are drawn, right? Yeah. It won't be the continuous. Since here there is an opening, sir, actually. So, what is metamaterial is nothing but it's a conventional copper or tin material, or same copper can be used, but there is no metal called metamaterial. So here you got to make a structure in such a way to attain the particular properties. Whatever thing we have seen, right? Negative permeability and negative permeability. Mu and epsilon, we got to prove it, sir, actually. Mu and epsilon, you got to prove, actually. So if you're able to prove that particular structure, then people will accept that particular material. So what they you got to justify as I have designed this particular structure. This particular structure containing the property of metamaterial that is helping me to reduce the size of the conventional antenna. So you can give the conventional antennas for, suppose if you are taking a 5 gigahertz or 2.4 gigahertz, you can take the particular antenna with the conventional methods or technologies. Then you can show your work. Then you can compare how much is the difference, and with the proof of this one, sir. Actually, the proof of this one. Okay.
Okay.
So with the help of this one, if you are able to justify it, you can do, sir. Yeah, this is one of the things, sir. And one more thing is going on. There is a metamaterial. Metamaterial is an extensive research topic actually. There is metamaterial. There is a topic called the clonk. Okay, invisibility. For that one, they are making 3D metamaterial, not this conventional based one. They are making 3D conventional. So if you implement that one, the invisibility, the clonk will be there. The optical also they're using, sir. Not only the antenna, the optical domain also they're dealing with the same metamaterial concept for terahertz also. Terahertz for invisibility purpose, for warfare applications actually, sir. So when we are going for
optical fiber fabrication, sir?
No, sir.
Is it
for warfare application in the sense, when you are going for battlefield, your radar should not be visible. Yeah. So what they are doing is they are trying to use a metamaterial based coating actually.
Okay, sir.
So your drones or your radar won't be visible to the opponent one. So based on your technology, you can hide your presence.
Yes,
But
sir,
you can do the battle over there. So that is a different one, sir. Actually, that is a clonk method actually.
Okay, sir.
So this is a basic, sir. Actually, one of the things we are dealing is basic. That is some kind of they're doing, sir. Actually, the clonk method. There is a pioneer called Smith actually. Victor Veselago is the first person proposed the concept of metamaterial, and Smith and one more few researchers carried out. In India also, we extensively carried out, sir, from NIT, Trichy, and IIT Danpur, and so many IITs, sir. Yeah.
Okay.
Yes, sir.
Thank you, sir.
Yes, sir. Yes.
Thank you, sir.
Participants, if you have any queries, you can discuss with the resource person now. I repeat again, participants, if you have any queries, you can unmute yourself and discuss your query with the resource person now.